The very interesting and a thing that we're going to use a lot in this course, and actually we already maybe used it, maybe not, but we're going to use it extensively, basically what this rule is telling us. It's a bit more elaborated, the rules that we see here. The rules say that I'm interested in a combination, not of a single, but I'm interested in combining n random variables, x1 up to n. And I'm combining them in a general way like this. This is in math, we call this a linear combination. For instance, that's what we do when we compute averages, right? When we compute an average, we take 1 over n of the first one plus 1 over n of the other one plus 1 over n of the third one. So this rule applies to averages. It also applies to weighted averages and different extensions of averages, but it applies also to averages, simple averages, right? So that's why it's a very important rule to us. The rule is telling us, the simple version, or simple part of it, which is the mean part of it, tells us exactly as before, that the mean of a linear combination is the linear combination of the means, right? So we just plug in the means and take the linear combination of the means. Probably something, as before, most of us would have done without thinking too much about it, which is fine. It's straightforward, the rule that holds true, fine. Here is then the extension of the variance part. And that is actually maybe the really, really important of this, because the first one we would just take for granted anyway, I would expect. But here's the very important. How can we find the variance of a linear combination of many things? Well, probably not surprising, it becomes not exactly the linear combination of the variances, or you could say a linear combination of the variances, but using the squared a's throughout. So it's a kind of a straightforward generalization of the simple rule from the previous slide. That is something that we will apply. Let's dig right into it. Start this example here. Here's an example. So this is in the planning office of, for instance, SAS. I studied with one back in Aarhus many years ago who had all her career in SAS, doing planning, different things. This is, of course, a very naive and simple version of a real-life situation, but I think it can give us a feeling of some of the concepts here. Let's assume that weight of passengers coming to an airline, an airplane, follows a normal distribution with, on average, 70 kilos for people and a standard deviation of 10 kilos. So we have a model saying that people are sort of most often between 50 kilos and 90 kilos, 2 standard deviations to each side. That is the model of the world now. Say, people come with an average of 70 kilos, most of them being 95% of people being between 50 and 90 kilos. 2 standard deviations to each side is 95%. That's what I told you last time, the feature of the normal. Now, here's the situation. We have a plane that takes 55 passengers. There is a limit to the weight. That's the situation. Cannot have more than 4,000 kilos. And for now, the only thing we take into account is the weight of persons. We ignore everything else. So just as a starter of trying to make some considerations here. Calculate the probability that the plane is overloaded, that we have a problem. So let's say y is total weight of passengers. And I think what we were asked to do is to find what is the probability that the total weight of passengers exceeds 4,000 kilos. Do you agree with me so far? Now the big question comes. To do this computation, we need to find the mean of y and the variance of y, right? To be able to do the normal distribution probability calculation, we need the mean and the variance of y. What are they? How can we answer that? Then I think, at least if I should answer this, let me see, I think I have, yes. What is the mean and variance of y? For this, I need to define to myself, I believe, what actually is y. What is y? Y is the total weight. I was given some assumption about the world here. Now I ask you. I don't ask you so many questions, since I'm so busy in telling you a lot of things that I forget to. But then again, you're 200 people, so it's difficult for me to have a nice chat with each and one individual of you in this context. But now I'm asking you to chat with me. What is y? Please?
I'd say 55 times x.
Could you repeat, sorry?
55 times x.
That's one possibility. Thank you. Do you agree? Do you all agree on this? I mean, thanks for saying this, but this makes the clue of this example just as it's supposed to be. You're going to be an expensive guy for SAS. Of course you won't, because after this lecture you'll never do this mistake again. This is not the correct answer, actually. And at the end of this, I'll of course show you how big an error this can lead you to. Let me try to be, I prepared the example in a way to have you sort of jump into it like this. I could have been more precise in my way of formulating the assumption in the situation. I could have been more precise, and I could have said, actually, since I have 55 passengers, I have 55 X's in play, right? And each individual of those follow a normal distribution, right? It's not that I didn't tell you this, but I didn't tell you as exactly mathematically as I've told you now. But I mean, in the real world, you can have people even throw it out just in words. I mean, things are normally distributed, then it's up to you to realize what does it mean in the context. Would you like to rephrase your suggestion now to what is the total weight? No? Fair enough. Anyone else who would like to give it another shot? Think about what the suggestion here tells us. This suggestion tells us, let's take the random weight for one person and multiply it by 55. Hey, these are not 55 clones of one person coming into this plane. It's not 55 times one person coming into the plane. It's, did we have a guess here?
1 times x plus 1 times x 55 times.
Exactly. So this is, let's say, not, but thank you very much. It was my point you made here. The thing is, the real, and now I used those explicit x1 up to x55, and that's what you say. Y is really the sum of 55 different persons, not a clone, 55 times clones of one person. That makes a hell of a difference. We'll see. Let's find the mean of y now. The mean, and that's now we need to apply the rules of that I gave you. What is the mean of y? Well, the mean of y, and let me use then, I can use these summation signs, it's just the same thing. What is the mean of x? that was 70 kilos, right? Or the mean of an individual x was 70 kilos. So let me be explicit here. Now I have a summation sign of 70, or I have 70 plus 70 plus 70 plus 70 plus 70, 55 times, right? That is 55 times 70 equaling, I wrote here, 3850. At least below 4,000 kilos. Phew, that's would not be nice if it was above. Then we had a high risk of overloading, right? At least it's below, but it's pretty nasty close maybe to 4,000 kilos. Now, you may still think a little bit, what the heck? Using this wrong suggestion would not make any difference here, actually. Because the mean of this one, let me say the mean of this wrong one up here, then we would apply another mean rule. We would apply the rule where we took the 55 out and take the mean of x, and that would be same thing. So, on the mean consideration, the wrong choice and the correct choice makes no difference here. But let's see what happens now on the variance. What does the variance mean here? SAS needs this variability to sort of be able to plan kind of overbooking. What is the risk of overbooking? How often do we, just to make an association here, they need to know the variabilities in the system to be able to know about how often will this planning strategy produce overbookings, for instance. And that is the variability in the system that will tell you how often will this happen. And how often this happens is the same as money price. So knowing about variability can sort of give you able to put in some limits to sort of say how often or how rarely should this happen. If you overestimate, if you're too cautious, if you believe that the system has a large variance, you would be too cautious. You would put the limits far away from the optimum, right? Whereas, so you should realize the proper variability to be able to earn money here also, right? So you should put yourself as close to the optimal choice as you can to be able to make a business of this, and not have too strict limits on yourself, then you cannot make business. Anyway, I'm maybe a bit ahead of the argument here. Let's go for the variance of y. Using the rule I just told you and using the correct choice of y tells me that would be variance of x1 plus, all of them, variance of x55. What was the variance of x, the individual x? That was 100 kilo, right? 10 to the square, 10 kilos squared. The variance was 100 kilos. I have, like before, I have 55 of those. So altogether, this is 55 times 100 kilo, right? Or kilo squared, I should say. So the variance would be 5,500 here. The real variance of this is 5,500. I'll finish this example and then we'll do the break, slightly delayed today. In the wrong situation, let me make this point here. In the wrong situation, what would the variance of 55 times x be? Then I use the other rule telling me that when I have a fixed number times a random thing, I should take this fixed number out and square it, right? That was the rule I told you. So this would lead to this answer. 50 times as big as the other one. You would believe that your variance is 55 times as big. If you square root that, it's 7 or 8, 7.5 times less risky, you would say. I couldn't find the English word here. So you would have a much too large feeling of the uncertainty in this system. So that would be very expensive on you if you want to make sure you're below. Let's finalize the answer of the probability of being overloaded. We could either do it explicitly in R, of course, or we could do this set transformation, telling me I should take 4,000 minus the mean divided by the standard deviation of y, which is the square root of 5,500. I get this number to be 2. Probability of going beyond 2.02, which if I use either table 3 or I use the p-norm function in R, would give me something like 2%. Roughly 2 out of 100 cases this will happen in this case. What if, let us just do this, finish the what if. What if I had taken it? What is the chance of going beyond 4,000 using a mean of 3,850 and using a variance, standard deviation of, let me see, 100 times 55 squared? That was the wrong, should emphasize here, wrong answer. Here, 39% of cases. You would believe that you would overload your plane in 39% of all cases, whereas the truth would be that you would only do it in 2% of cases. That makes a drastic, dramatic change in how you want to deal with this in your everyday. And of course, I mean, if you planned like this, it wouldn't take a day or two until someone out there would say, hey, what's going on here? We are much off pitch here. Now, this is a naive example maybe, but things like that are going on in more complicated disguises all the time, right? And you need to face these things. And the thing about variances of sums of stochastic variables are a key issue. It's a key issue in understanding variability of systems and using it. And it's going to be a key thing for our statistics part of the whole course. So, sorry, a bit late, but let's do a 15 minutes break here now.